It is essentially something that does not think, it is not self-aware, and it's just electrical signals and pulses on transistors that are beat into a pattern that when they get information or electrical signals, it uses this pattern and equations and everything to output something that looks very close to the data it got. Now to us, it assigns meaning. We assign meaning to the data and information we get out of this machine learning algorithm or this artificial intelligence, but it is not self-aware. It is just electrical signals doing things and making guesses and predictions at what data it got, and it's making a guess at a token that seems to be most likely correct. Okay? That's all AI is. So you got what you came for. Now, if you want to stay and go with me in depth in how this came to be in the first place, then come with me on this journey. Hey, this is the AI environment, the AI playground, where we discuss AI, artificial intelligence news, and also skills that help you build and work with machine learning models and programming in Python. Okay? So what I'm going to do is cover a little bit of history as I know it, from my personal experiences and how I would explain artificial intelligence. So here, I'm going to start from the very chip level, okay? I'm talking about CPUs. If you're not familiar with CPU, a CPU is a central processing unit. And then we will get into GPUs a little bit, and then TPUs. And, this is going to be a casual lecture, nothing crazy, formal, or anything like that, okay? Let me make sure my brush size is not too large. Let's see here. But not too thin either. Okay. Okay, I think this is a decent brush size. So first, everything starts with actually the transistor. The transistor, which was made in maybe the 40s, 60s, I can't quite recall, is the fundamental building block of all machine learning and artificial intelligence for right now. The transistor looks like this. What happens is you get a voltage that is applied to, you have many transistors actually. So this is a MOSFET, a metal oxide semiconductor field effect transistor. So essentially what happens is a voltage is applied to this transistor. Really, the transistor looks like this. It looks like a little trough or thing that has this P and N-type material. It's positive and negative type semiconductor material that when a voltage is applied to this gate here, there's a gate and you have a voltage applied, it opens up a channel at the bottom in this material. You can have P-type or N-type material, it just depends, and that will dictate the kind of voltage you apply to it. When this voltage is applied to this gate of this material, then you have the ability for a current to flow through that material. If you have, say, another voltage source, a voltage source like a battery attached here, and a path for it to go to ground. Okay, so this is our battery or voltage source. This is this ground or some other part of a circuit, lower potential of a circuit, and then you have this material, a semiconductor material, that when a voltage is applied to it, it can allow current to flow through. To get some kind of voltage operating on here, you want a resistor. Okay. Now this is a little messy, but don't worry about it. I'll just clear the screen. So we have our little tub. It allows current to flow through. You have a resistor. It goes to ground. If you have no idea about electrical properties or anything, that's fine. You can check out my other channel where I discuss electrical engineering and electronics fundamental concepts. And then you have this battery of sorts, or voltage. As long as the voltage is applied somewhere here, and then there's a difference in potential like down here, and you have a path, a conducting path for electrons to flow or holes to flow, then you have current flow. Current going through some kind of resistance instigates another voltage, a voltage drop. Okay, Resistance impedes the flows of electrons. They can still flow, but they flow more slowly, and a potential is built up. Okay, why is this important? This is very important because this is how we're going to get into pretty much the fundamental building blocks of machine learning models. Now, how can this channel be turned on or off? Well, it can be turned on or off with a voltage applied here. Okay, this device is our transistor. Okay. When the voltage is applied here, let's say we apply, just enough voltage to turn this thing on. Current flows through this resistance, or really it's up here, this resistor. Either way, just work with me here. If we put this voltage across through this resistor on a time scale, when the transistor is turned on or allows current to flow through, that voltage starts to go up on this resistance. When current is turned off, when that channel is cut off, current stops flowing. It decreases linearly with time, very quickly, very, very quickly. Okay, on the order of fractions of a second, fractions of a millisecond in some cases, depending on how fast you're operating. Okay, and then we have this thing. This is the voltage seen across this resistor, which really should be over here. Or it could be down here, either way. And then this resistance, this is our transistor. This gets now into what's 1 versus a 0. Okay, what's 1 versus a 0. Here we're in the binary realm. We've gone from transistor to binary. A transistor you'll normally see looking like this for the symbol to simplify it. Same thing, we have our resistor up here, voltage here, some kind of, now I'm putting the resistor up here where it's supposed to be, or you could put one down here, and then there's a lower potential. And the voltage I showed you earlier that can turn this thing on or off, this transistor on or off to allow current to flow through. Okay, this generates some kind of pulse, right? With the voltage being, say, 1.1 volts or something, or 0 volts. Now, these levels you're going to see in DDR3 RAM. In CPUs, they could be lower, higher. And in, just DDR4, you're looking at 0.9 volts. I think it is. Don't quote me on that. This is actually a voltage, but for code purposes, we need some way. We can't look at voltages all day as programmers and developers and say, oh, we totally understand what's going on here. We need some way to encode that. So we say, okay, it can only turn on or off. We'll call that a 0 if it's low enough, and we'll call it a 1 if it's high enough. So now we have a CPU that has billions and billions of these transistors, right? Billions of them. Billions. 57 billion if you're looking at the Apple M2 chip, I believe it is. And then all these transistors are generating really voltages, tiny little voltages, but zeros and ones now. You have your CPU, your cache and everything, right? This is your binary. The binary, this zeros and ones, is based on a power of 2 system. So 2 to the 0th power is 0. 2 to the 1 power is 2 to the first power is 2. Okay. 2 to the second power is 4. 2 to the third, 2 to the fourth, and so on and so forth. These ones and zeros represent these powers of 2 because you only have 2 options to choose from. Humans, we have many power systems. The 8 to the power of n system. Currently, we use most of the times 10 to the base 10 system. 10 to the power of 0, 10 to the 1, 10 to the right. 10 to the 1 is 10, 10 to 2 is 100, 1,000, so on and so forth. Computers and machines, they're operating on base 2 system, zeros and ones, which is actually some voltages. Okay, why is this important? Because the programmers, they decided, well, ones and zeros, zeros and ones and everything. This is where we get into another topic, assembly. The programmers looked at these ones and zeros and they said, okay, we can look at this all day, but this is really hard to process and understand and make sense of. Hard to make sense of. So they said, we need to translate this into something. There are a number of things you can translate it to. One of the languages is called assembly. This is where you understand the organization of your chips, your CPU, your RAM, and then we can turn these ones and zeros into things like hexadecimal code, so base 16, to condense the information into letters like F, A, C, B or something like that, and zeros and whatnot. Okay. Hex allows you to condense a lot more information into a tighter compact form. This is still alien. I mean, it's not alien. We created the system, so we know how to interpret it. But this is too complicated. So they decided these hexadecimal codes, let's give them nicknames. We'll call it a move function. For a hexadecimal code, these are just electrical signals, mind you, ones and zeros. The move code, if we put it here into our chip, our central processing unit, our microcontroller, this will put some information. It will perform a command. Okay. So something like FF0 whatever, blah, 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 to this set of information pushes information into RAM at this location into memory. Okay. At such and such location into memory. And then you have more of these move commands, and then pull and push, right? To now you have this language that's that's easier to read, that is directly translatable to hexadecimal code, because these are just nicknames for hexadecimal code. And under the hood, these are actually hex codes, and under that hood, those hex codes are actually binary ones and zeros. And behind that, those are just electrical signals. This is all electricity. Okay. Interacting with chips and transistors to manipulate their electric fields, to have them do something. Mind you, this entire time, the chip is not aware. It has no idea what's going on. Okay. This is our initial programming. Now, engineers, they're like, hey, while this is nice and all, we have about 1,000 statements. Like when RAM was really cheap and small, 32 kilobytes was large. You're only working with 2 kilobytes, in some cases little bits or what have you. And it's like, but RAM and memory started getting larger. Disk space started getting larger. We're talking about 2 megabytes now. Now you get 1 gigabyte as time progresses. Okay. So then we figure, wow, we can't write 1 million instructions to just store some information on a floppy disk. There has to be a better way in assembly. So engineers decided, and developers decided, early electrical engineers, they're like, we need to further translate this machine code into something we can interpret. So then you get into languages like Fortran, which was my first language, Fortran 90. Punch card for codes. I don't remember which era that was. I don't know if it was the 80s or 60s or what have you, or 70s. And then you have C code. Now the thing about C is that, and Fortran's good for mathematics, by the way. It's really good. Okay, the thing about C code is that it's close enough to assembly, but also close enough to human understanding that you can still understand what it's doing in assembly, but you can pack a lot more. You can pack more density into the C code in terms of like assembly instructions into the C code. But the C is still readable. You have your main statement, your main file. You can store things in files now. You can do loops in C, whereas in assembly, you had to do loops quite manually. Line, do this, do this, do this. You can still do loops and do like a do of sorts, and it will loop again. But it was rather convoluted, hard to follow. C, you just got a for loop for I, do this, equal or less than 3 times, do the thing, blah, 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 execute, done. You can return things and everything. So that's the beauty of C in programming language. Only problem with that is that now is not directly translatable into hex, not in all cases. So now the C needs a compiler. The compiler figures out, hey, what you got? You got this for command? Okay. I'll translate that to assembly code, or I might just directly translate that to machine code. And hex is really just our version of ones and zeros, which is really just our interpretation of electrical signals. Okay? Code is just electrical signals. The electrical signals then go back to the chip, CPU, GPU, whatever, and then the chip does its thing and processes that and spits out whatever we tell it. Now, this gets into programming logic. We've handled C, and now let's get into programming language logic. When it comes to programming logic, the machine needs to do a task, right? Let's say we want it to give us a cup of coffee. Now, I'm more of a tea drinker, herbal tea, because caffeine is not really my thing now. But anyway, give us a cup of coffee. The cup of coffee, the machine doesn't know what coffee is. It doesn't know what a cup is. It doesn't know what give or us is. It doesn't know anything. It has no awareness. It's electrical signals. That's all it does. That's all the chip can process. Okay. So now we with our higher intelligence say, oh, well, we need to tell it what a cup of coffee is. Like, well, it doesn't know. Well, okay. We're just going to give it instructions. Does it really need to know what a cup of coffee is to complete the task? Does it really need to know any of this to complete the task? No, it can't know anyway because it doesn't have awareness. The machine, it's electrical signals. So the smart engineer, the smart programmer, early electrical engineers became the programmers, I would say. And then logicians and whatnot, mathematicians, many people became programmers. They said, hey, let's give it specific instructions like we've always been doing to do this, do that, do this and that. It is not aware that it's storing things into memory. It doesn't know where memory is. It's just electrical signals. But we have higher order instructions now on top of the instructions. Oh, by the way, before I get into programming, let's discuss a bit about firmware. The infrastructure that tells the processor, the CPU, the RAM, the GPU, the chips with the I2C communication protocols and everything. They have many, many different protocols that they use to pipe all this information around to different chips on the computer motherboard. Now, mind you, all of this code is strictly dependent on the levels of the electrical fields, the voltages and currents. If the voltages and the currents are not accurate, if they're not doing what they're supposed to do, if they're not at the voltage level they're supposed to be at, we're going to have a problem. And who manages that? It is the electrical engineer, the electrical and electronics engineer, who carefully selects these devices. The manufacturers of these devices make sure that they have certain performance, rise time, slew rates that can meet the electrical demands of the programming that needs to get done, right? And all of this fails without the printed circuit board. So let me clear this real bit. I'm making a little detour. All this depends on the PCB, the printed circuit board. What is a printed circuit board? It is literally your computer motherboard. It is anything that is an electronic device. If you crack that thing open, if you open this keyboard I have, this pen, this mouse, you break off the enclosure, it'll still work, It'll still work as long as it has this printed circuit board with components on it that are sending electrical signals. This PCB is the foundation of all technology devices, electrical engineering, and not all electrical engineering, but consumer electronics, any electronic device, anything that needs to be programmed, it must. Well, it doesn't have to have a PCB, but in most cases, because you can use electrical wires and signals. The PCB just makes electrical wires and conductors more compact. But anyway, the PCB or whatever electrical system is carrying those signals must be intact and worked very well electromagnetically, because you're piping around electromagnetic fields operating at the speed of light. Well, half the speed of light once they're inside of the dielectric material. Then you have conductors and traces that guide the waves through the non-conductive material. And these electromagnetic waves and fields are dictating what kind of electrical signals are happening. Without the printed circuit board, you do not have machine learning algorithms. If you're interested in PCBs and whatnot, learning a bit more about those, you can check out my other channel and my videos on that. Okay, so now coming back up to the firmware engineer ensures that the machine code used to pipe information to all these different chips is done well and is intact. The low-level computational operations. Then the programmer, it could be a software engineer or a developer or programmer, uses the higher level C language or Python or what have you, but C is closest to assembly in my opinion, that's why I like it so much. Says, hey, now we need higher level tasks. Now that it's akin to the how the synapses have their electrical signals and the wiring and everything. That's your I2C bus. That's your PAM signals and everything. That's your RGMI signals and all these things. Your I3C USB. That wiring, those protocols that are used, that's akin to our brain, our CPU, being connected to our arm or being connected to our spinal cord a specific way. It needs to use a certain protocol to communicate with different parts of the body. Okay, that's all set by the firmware engineer. Say, hey, make sure you talk to this one, that one, blah, 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 blah. Now, as far as overall commands, we're not commanding anything yet. This is our lower level operating system. Okay, the higher level operating system now is you have your firmware and your operating system. Now that's the same as like Mac OS. I'm on a Mac. You have Windows. I know I'm jumping around a little bit, but stick with me. Mac, Windows, we have the firmware, the OS. So see, all of this is the PCB, the protocols. Goes up to the firmware, goes up to the OS. Oh, and the protocols have really the PCB and the hardware layer for the chips, and then your protocols, then your firmware, then your OS. Your OS is the way you think, essentially. Maybe you're thinking like a Mac OS, or maybe you're thinking like Windows. Maybe you're trendy and you're not trendy. I'm just playing. Okay, just don't take it seriously. All right. Or Linux. It's the way you process information, just in general. On top of this operating system, now you can bypass this and speak directly to firmware, which is embedded systems. I won't get into all that. Okay. In the operating system, you have your higher level C language. The operating system and the C language, all of this is translated by some compiler and whatnot. Your compiler is translating that all back to machine code, ones and zeros, electrical signals and pulses. Okay, now back to the coffee cup example. Having that cup of coffee, The machine has not a clue what the command means. Just like how you can instruct someone to raise your arm. Well, I know, I may not even know what arm means, but I just know what this thing is. And you say, and you show me, go like this, grab this. Because I know what these are, because my firmware is intact. I can do these things mimicking. I don't need to know what the coffee cup is. I don't need to know what anything else is. As long as my electrical signals are pulsing, I don't need to know anything. I haven't learned anything. It doesn't necessary. That's what the programmers do. They program the commands. Okay, that's a bit messy. They program the commands. The compiler translates this command to machine code. The machine, the CPU, and the RAM and everything, they execute on the tasks. They do not know what they're doing. They can't know. They don't have sentience. They're not aware. Okay. You say, as the programmer, hand me the coffee cup. Boom. Now, let's say the conditions change. You get a block in the way of the path that you're walking to hand the coffee cup. You bump into it, and then coffee spills over. And it's like, dang. Okay, I need to account for that situation. Okay, in the second situation, if you see it encounter a block, walk around to the right. Okay, it walks around to the right. That goes well. There's another block to the right. It's like, what's going on? Okay, now you have to program for the third scenario, and the fourth case, and the fifth case, and the whatever case and scenario. Now you as the programmer are thinking for the machine, because the machine can't think. It can only follow instructions. The machine following the instructions and you managing all of the conditions in which the instruction applies. That's the job of the programmer. The machine has no awareness. Eventually, you as a software developer and programmer, you consider all scenarios, and 99% of cases, you can translate that into machine code that if this case, if that case, blah, 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 do this, blah, 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 everything. The machine can accomplish a task without knowing anything. So that's why people say, code does exactly what you tell it. That's literally true. It's electrical signals. Okay. It's not even following instructions. It can't follow instructions. You are putting instructions and electrical signals into it to determine, to have a certain outcome. Why is this important? Because now we finally get into artificial intelligence. We've already established that the machine only has electrical signals it can work with. It has no awareness of the coffee cup, but it can still achieve certain tasks. That's why what your laptop and machines do is only as good as the electrical engineers that work the printed circuit boards and the electrical components, because none of this works without that stuff anyway. Proper management of electromagnetic fields. Your firmware engineers who make sure that everything is talking to each other, otherwise the commands won't make any sense. The programmers who think about and think ahead of the commands that once they test it and everything, it works out and the machine does what it's supposed to. The machine still has no awareness now. Now we get into artificial intelligence. How do we have the machine understand? It actually doesn't understand anything. How do we have the machine output or interpret data that we give to it? How do we make it recognize things? It can't recognize things. It only makes models or guesses of things. So it doesn't even recognize. It has no self-awareness. It's just electrical signals. But we say, hey, we need it to understand what a coffee cup is, or at least have some kind of algorithm. What is an algorithm? An algorithm is a bunch of pretty much mathematical equations and matrices and everything. The equations, they say, hey, you give us some data, some numbers. We're going to crunch that data and numbers in such a way and multiply those equations in such a way, these matrices in such a way, that when we spit out an output, it has a certain probability or likelihood. Mind you, programming is deterministic and AI and machine learning is probabilistic, along with code, in terms of its output. These are equations that adjust themselves. They move and they gyrate according to the data that they get. Okay? They move and they do things. No awareness, it's just mathematicals. It's math. Pushing out numbers that hopefully, depending on how the machine learning engineer, now we got machine learning engineers, has programmed the algorithm is like, hey, these electrical signals transform these electrical signals to produce these electrical signals that hopefully produce something similar to the electrical signals we gave it to it. These electrical signals have no clue of what's happening. The machine learning engineer does, though. And so does the programmer. Oh, okay, not the AI, the programmer. The machine is just doing electrical signals. Electrical signals go into electrical signals that were programmed by humans to produce more electrical signals that hopefully match the initial electrical signals that were given to it. No idea, this AI. Okay? Now, when the machine learning models and algorithms spit out data that looks surprisingly, very strikingly similar to the original data, 0, we as humans, as interpreters, we say, hey, this looks about right. But it depends on how good the algorithm is. The algorithm is not perfect, not always, a lot of times. So it may predict something that is completely off base. The way that this machine learning algorithm is built dictates its perception of reality. What we see is this machine learning algorithm's perception of reality, this data that comes out. The more often it matches reality, the better the model is. It's perception, not understanding, not awareness. Likeness, even. It's similar. I'd say it's similar to how humans perceive things. And this is just pattern recognition. This is not awareness mechanisms or emotions or anything like that. Logic and reasoning and all that stuff. We have multiple intelligence. We have at least 6 or 8 intelligences in us. We're just trying to get this to be good enough to match our pattern recognition. Now, we have many different things, convolutional neural networks, artificial neural networks, XGBoost, ARIMA, all these different things. GPT, generative pre-trained transformers, and all that stuff. I won't get into all that. I'm just letting you know what a machine learning model does and is. This data, once it looks similar enough to us, we say, oh my goodness, this thing is alive. It's not. It's electrical signals. Manipulating electrical signals. Because it looks similar, we assign life to this thing. It has none. I mean, obviously it doesn't have life, but And this is one of our 8 intelligences at work that is trying to mimic our model. Okay. So that's essentially machine learning in a nutshell as far as models are concerned. Machine learning engineers and programmers and developers are working furiously, tirelessly to have more data processed in parallel and at the same time. So we have tons of GPUs. Okay, GPUs can process simultaneous transactions. CPUs can only do one instruction at a time, essentially. And you can have multiple CPUs, but each CPU is still only doing one discrete thing at a time. But they can do it very fast, very quickly, 3.5 gigahertz and so on and so forth. Billions of times per second. Now, if you imagine can do something billions of times per second, but in parallel, all at the same time, that's your GPUs. That's why NVIDIA is winning right now. Any company that can get in the chips and arms race, the chips arms race is in the AI arms race to compete for one of the human intelligences. Isn't that insane? Now, I'm not saying that we can't kind of mimic things. When you have tons of humans together, They can do anything. Or on the same accord, you can do pretty much anything. When you have thousands of humans together, and when you put multiple AIs together that attempt to mimic different parts of the human intelligence all at once, now you have something very powerful, and that starts really to look a bit more like maybe this thing can reason a little bit. Maybe it can, okay? So the better we are at modeling, coming up with models that can translate these different emotions, as long as we can translate these different things, these intelligences of the mind. Now, if anyone takes this as my idea, okay, the intelligence of the mind, in addition to just pattern recognition, now you're getting closer to AGI. Mind you, we're still struggling with pattern recognition for languages, for, okay, LLMs and everything. Humans, we can do all that stuff. We can recognize experiences, patterns, language, all this stuff all at once with one or a couple pattern recognition tools of our one intelligence of 8 or more. I keep saying 8. I don't know how many intelligences there are. Okay. That's why I believe AGI, while what we are seeing may look like AGI, I think it's further away than people might think. Now, I haven't a clue. How close we are. Maybe we are closer. But I think we are at least 10, 15 years away from seeing, so maybe 2035 to 2040, from seeing the first remnants of true AGI. True AGI. What we're seeing looks like something very intelligent. Okay, with robots and everything. Recent news. Check out my video on recent news of a robot that can process instructions and everything. And again, I might be underestimating artificial intelligence, but this is my opinion. I'll stick to it and then I'll see what happens. Okay, that is my summary on machine learning. There's a lot more I could have gone into here, but that is the brunt of it. Check out my other videos if you want to get into using Python for data analysis and machine learning, or understanding or news in AI. Okay, and have a good one.